Blockchain technologies are revolutionizing the way transactions are recorded and processed. Their decentralized nature ensures that trust is established without relying on a central authority. Understanding how blockchain technologies work requires an examination of various key components. Decentralization is a fundamental characteristic of blockchain technologies. Unlike traditional databases managed by a single entity, blockchains operate across a distributed network of computers known as nodes. Centralization poses several risks, including data manipulation and single points of failure. By dispersing data across multiple nodes, blockchains enhance transparency and resistance to censorship. Each node maintains a complete copy of the blockchain. Therefore, all network participants have access to the same information. This decentralized structure promotes trust among users. Even if one node fails or is compromised, the overall integrity of the blockchain remains intact. The consensus of the majority ensures that accurate data is maintained, as changes are subject to validation by other nodes. Each blockchain consists of a series of blocks, which are the fundamental units of the technology. Understanding the structure of these blocks is crucial for grasping how blockchain technologies function. Each block typically contains a timestamp that records when the block is added to the chain, a cryptographic hash of the previous block, establishing a secure link between them, a nonce, which is a unique value repeated only once, used in proof-of-work mining, and a list of transactions or data entries, which represent the activities recorded in that block. The timestamp plays a critical role in establishing the chronological order of transactions. Meanwhile, the cryptographic hash provides security by ensuring that any changes to the block's content would render the hash invalid. This builds a chain of trust from one block to the next. Validating new blocks and achieving agreement among the distributed network is pivotal. This process is governed by consensus mechanisms, which determine how nodes reach an agreement. Two widely recognized consensus mechanisms are proof of work, POW. In this paradigm, nodes, often referred to as miners, compete to solve complex mathematical puzzles. The first miner to successfully solve the puzzle gains the right to add the new block to the blockchain, receiving rewards typically in cryptocurrency. Proof of stake, POS. This alternative mechanism selects validators based on their ownership of the cryptocurrency. By staking their coins as collateral, validators earn the opportunity to validate transactions. POS tends to be more energy efficient than POW, significantly decreasing environmental impact. Analyzing the trade-offs. While POW bolsters security through competition, it often requires significant computational power and energy. Conversely, POS reduces energy consumption but may concentrate power among wealthier stakeholders. Understanding these trade-offs helps users select appropriate blockchain technologies for specific use cases. Cryptography in blockchain technologies. Cryptography is foundational to the security and integrity of blockchain technologies. It protects sensitive data and ensures that transaction details remain confidential. The role of cryptographic algorithms. Each block is linked through cryptographic hashing, ensuring that even minor alterations trigger changes in the subsequent blocks. This property reinforces the immutability of the blockchain, ensuring anonymity and security. Public key cryptography enhances user privacy and security. Users possess a pair of mathematically linked keys, a public key for receiving assets and a private key to authorize transactions. This dual-key system facilitates anonymous transactions, as identities are not disclosed during transfers. Immutability as a core principle. One of the most significant advantages of blockchain technologies is their immutability. Once added, blocks cannot be altered without consensus. The implications of immutability. Immutability instills confidence among users, as it guarantees data integrity. Altering any block requires recalculating the hash for that block and all subsequent blocks. This requirement creates immense difficulty for malicious actors aiming to compromise the blockchain. Building trust among users. Due to this characteristic, blockchain technologies are compelling for applications requiring trust and reliability. Entities can engage in transactions without fear of data manipulation, fostering confidence in the system. Smart contracts and their functionality. Smart contracts represent another innovative feature of blockchain technologies. These self-executing contracts automate processes based on predefined conditions. Mechanism of smart contracts. When specific conditions are met, the smart contract executes automatically, eliminating the need for intermediaries. For instance, in a supply chain scenario, a smart contract could trigger a payment once goods are confirmed as delivered. By automating processes, smart contracts minimize delays and reduce transaction costs. Furthermore, they enhance operational efficiency, enabling seamless interactions between parties. Blockchain technologies that incorporate smart contracts find use in various sectors, such as finance, real estate, and insurance. This functionality extends the capabilities of traditional contracts and promotes innovation. The applications of blockchain technologies extend beyond cryptocurrencies. Industries across the spectrum leverage these systems for various purposes. In finance, blockchain technologies power cryptocurrencies, enabling peer-to-peer transactions without intermediaries. Enhancements in payment processing speed and security are driving adoption. Blockchain is instrumental in supply chain transparency. It facilitates tracking goods from production to delivery, thereby enhancing accountability and minimizing fraud. Secure and immutable health records contribute to improved patient care. Blockchain technologies allow for real-time updates while safeguarding sensitive information. From voting systems to identity verification, the possibilities are limitless. Each application benefits from blockchain security, transparency, and efficiency characteristics. In conclusion, blockchain technologies represent a paradigm shift in transaction processing and data management. By harnessing the power of decentralization, cryptography, and smart contracts, these systems pave the way for transparent and immutable records. As organizations continue to explore blockchain technologies, the potential for innovation is immense. Recognizing the implications and applications of these technologies will be critical in navigating the future landscape of digital interactions.